Hi, I'm Ren Hong. Today I'm going to present Impossible Staircase. This work is done by me and my fellows from National Taiwan University. Impossible Staircase is a virtual reality system that allows users to experience vertical real walking infinitely in a limited physical space. It achieves this by using a lifter and a one-level scaffold. Users wear HMD climb up the scaffold by real walking on a stairway, then are reset to the ground by the lifter imperceptibly. By repeating this process, they perceive an illusion of climbing an infinite number of levels. Long time ago, VR was only possible at labs. With the advancement of VR technologies, everyone can now experience VR at home. Many people then envision a future of experiencing VR anywhere. Recent VR technologies such as Oculus Quest just aligns with this direction. It enables immersive experiences to deploy nearly anywhere as long as there's a space. To enhance immersion by real walking in VR in a limited space, researchers have proposed a body of research on walking-based local motion devices. Some researchers also have looked into simulating walking on uneven surfaces. In addition to hardware solutions, there are many techniques to achieve local motion in VR within limited space. These techniques can be broadly categorized into teleportation, walking place, and real walking. Studies have shown that real walking is still the most immersive and natural way to navigate in VR. To enable real walking in VR anywhere, recent researchers have proposed systems that incorporate surrounding physical environments into virtual experiences to prevent users from collision. Some systems achieve real walking under uncontrolled space that reflects dynamical changes of surrounding physical environments. However, vertical real walking such as walking on staircase while wearing an HMD has not been fully investigated. That is, along the line of deploying immersive experiences anywhere, we're looking to vertical real walking VR. Especially, we're looking to a common space configuration in buildings, staircases, and elevators. We set up an experimenting environment in our lab with a lifter and a scaffold to approximate a staircase and elevator respectively. With our setup, we built a vertically real walking VR system, Impossible Staircase. It allows users to climb a virtual tower with infinite number of levels. Our system achieves this by generating imperceptible and reverse motions using the lifter to reset a user's position, using delay mechanism to buy more time and to move and reset the lifter, procedurally generating an infinite number of levels. In Impossible Staircase, the lifter generates imperceptible motion when sending users back to the ground. From a user's perspective, they perceive themselves staying still at the same level in VR. Here shows an example. After climbing the stairway, the users arrive at a new level and sees a hanging cargo blocking his way. He watches the cargo moving and staying still until the cargo drops, paving the way for him to pass through. While in reality, he is sent back to the ground by the lifter imperceptibly. Moreover, Impossible Staircase enables more drastic mismatch, which reverses the user's perception of motion. We achieve this by tuning our lifter's motion profile to generate a burst of acceleration followed by the imperceptible motion. When users are shook down by the lifter, they perceive themselves elevating in VR. This further enhances the flexibility of virtual level design. Here shows an example. The user takes a virtual elevator to the 40-meter tall level. The user steps into the elevator and then sees themselves being transported upwards. At the same time, in reality, the lifter is actually moving downwards and sending him back to the ground. Inspired by substitutional reality, we also explore a range of mismatching visualization of the physical staircase geometry without significantly affecting real walking experience. The visualizations are categorized into three characteristics: skin substitution for maintaining thematic consistency, hash forming for generation. You can see here a pile of random generated objects. Animacy for interactivity. Here, the rising pillars interact with the user steps. Here are more implementation details. Here we show a detailed look of how our system implements a stealth illusion. After the user walks from the first floor to the second floor, he is stopped by a delay mechanism. Here he has to break the door. While he is breaking the door, the surrounding scene follows the movement of descending lifter so that he doesn't visually perceive the motion. After the lifter arrives at the ground, he walks forward, and a new level appears once he leaves the lifter. To enlarge the room vertically while preserving the realism of climbing, we also incorporate impossible spaces to place two vertically overlapping enlarged rooms. Let's talk more about how we implement the control unit of the lifter. We use a hydraulic lifter in our system. The lifter goes up and down by pumping in or releasing oil from the hydraulic. To control the descending motion of the lifter, we assemble a control unit to control the hydraulic valve. A servo motor is used to rotate the valve to throttle the releasing speed of oil from the hydraulic cylinder, and thus control the descending speed. With the above system, we control the lifter speed to achieve imperceptible and reverse motions. Here illustrates the lifter's velocity under the imperceptible motion. Once the user stands on the lifter gradually accelerates and stops accelerating when reaching a speed threshold. The lifter then speeds down when it's close to the ground. The reverse motion is achieved by controlling the lifter to ascend for 2 seconds to simulate the initial motion of a real ascending elevator. Afterwards, the lifter moves following the control scheme of the imperceptible motion. For the detail of control scheme, please reference our paper. To prevent users from entering dangerous zones, interactions can be incorporated to maintain enjoyment. Here demonstrates some interactions when users are sent to the ground by the lifter, and also interactions when the lifter is ascending back to the top. In order to achieve infinite gameplay, we implement a procedure generation algorithm. A state diagram determines what type of the story occurring when a user enters the next level. The story-related game prefects then are randomly spawned. We conducted a preliminary user study to validate our system and recruited 8 participants. No participant has seen the experimenting environment before the experiment. The task for the participants was to walk through our demo experience. In our study, we found that different visualization of the staircase don't significantly influence the participants' walking performance, so more staircase visualization can be incorporated in level design. All the participants did not perceive they were sent back to the ground by the lifter. 7 participants felt taking a rising elevator in VR realistic. One user thought mismatch of foot shape and size between VR and the real world decreased the walking balance. From our study, impossible staircase enables vertically real walking given limited physical space. However, our current system limits the level design. Infinitely walking down cannot be achieved due to the lifter's constant upward lifting speed. Current system requires manual labors being safety guards. More responsive visual warnings and more automated safety devices may enhance safety. In the future, we will look into incorporating redirect walking into our system to allow more flexible experience design and deploying the system in real buildings. Thank you.